Welcome to ECO2Fuel Perspectives, the podcast that brings you insightful conversations at the forefront of sustainable energy and the fight against climate change. Brought to you by the ECO2Fuel Project, an innovative initiative under Horizon 2020's Green Deal program, aimed at revolutionizing the production of economic and sustainable liquid e-fuels and chemicals. Your host, Dr. Schwan Hosseiny, Project Coordinator of ECO2Fuel and CEO of Cutting Edge Nanomaterials, will guide you through this intriguing world of sustainable energy. We'll delve into pioneering research and inventive solutions that are reshaping our future. Join us as we engage with top-tier experts and stakeholders to dissect and unveil the latest breakthroughs in carbon capture and utilization. We'll navigate the complex interplay of science, technology, and policy, explore challenges, celebrate triumphs, and shed light on the potential of carbon capture and utilization technologies for our environment, economies, and society at large. Whether you're a passionate advocate, a dedicated researcher, an influential policymaker, or just curious about the future of energy, you're in the right place. Prepare to broaden your horizons, rethink established paradigms, and gain a refreshing perspective on the journey towards a sustainable, flourishing world. Don't forget to subscribe to our podcast for the latest episodes, and join us on our social media platforms for engaging conversations. Together, we can help sculpt a cleaner, greener future. I'm delighted to have you along for this journey. Welcome to ECO2Fuel Perspectives.
Hello, everybody, and hello, Antonino. I'm very glad that you're joining us today to our podcast. And I'm very happy to have you on board in the consortium of the ECO2Fuel project. Antonino is Dr. Antonino Salvatore Aricó, is presently director of the Institute of Advanced Energy Technologies of the Italian National Council of Research, CNR Italia. He was head of the electrochemical process for energy conversion group at the CNR Italia, and was involved in research programs related to the development of energy technologies with special regard to electrocatalysis, electrolysis, fuel cells, CO2 conversion, solar cells, and batteries. Dr. Antonino Salvatore Aricó is also covers the role of Italian representative as the state's representative group, SRG, of the Clean Hydrogen Joint Undertaking. Dr. Aricó has published more than 368 articles in international peer-reviewed journals and authored 13 book chapters, and has an impressive H-index of 68. Dr. Aricó has been coordinator and responsible scientifically for about 50 projects, including new national and industrial funded contracts. Antonino, I'm very happy to have you on the consortium of ECO2Fuel. Somebody with your experience and skills is definitely helping this project to succeed. And now I would like to give you the word to tell me a little bit more about CNR Italia. And then we have a lot of interesting questions that I would like to ask you for the ECO2Fuel project.
Thank you very much, Schwan. Thank you for your introduction, and also thank you for this opportunity to collaborate with you and with the consortium of the ECO2Fuel project. It is a great pleasure for me to contribute to this research on carbon dioxide reduction, recycling of carbon dioxide. Regarding my institute, this is the Institute of Advanced Energy Technologies, and it belongs to the Italian National Council of Research. CNR is the largest Italian public research organization, and its duties are to carry and promote, spread research activities in the main sectors of knowledge, and use this research, scientific and technological, and knowledge to improve, to assist the country and to assist the social development of the country. My institute belongs to the Department of Engineering of the Italian National Council of Research, and the activities that are carried out in this institute essentially regard the green hydrogen in general, especially electrolysis, fuel cells. We have a strong research activity on batteries, on heterogeneous catalysis, and in general on renewable energy sources. Essentially, the CNR ITE activity is based on a mixture of basic and applied research, and this is carried out through a multidisciplinary approach. So we are essentially focusing on electrochemical energy conversion technologies, also taking advantage of our expertise, our knowledge in material science, micro and nanotechnologies, polymer science, and system engineering. And that's all for my institute. I tried to provide a brief description of our activities.
Thank you, Antonino. It's a very broad activity field, and so in the ECO2Fuel project, you're also contributing in many work packages with your experience and skills. So we have asked for a couple of questions to be answered by you, and so I would like to start with the first question. So conversion of carbon dioxide into fuels and feedstock chemicals using renewable energy to reduce greenhouse gas emission has obviously gained a lot of momentum in the recent years. So which are the main perspectives and challenges of this process in your opinion?
Thank you so much, Schwan, for this question. Carbon dioxide recycling can avoid the net carbon dioxide, net CO2 emissions in the atmosphere, and of course will contribute to achieve carbon neutrality. And this is the key aspect of this process. Of course, this process can strongly contribute in reducing the negative effects of the climate changes and global warming. In particular, I would say that this process can help the transition towards a decarbonized energy system, and at the same time will assure energy security. That is an important aspect. Carbon dioxide and water can be thus converted into renewable fuels. In principle, using low temperature co-electrolysis into these can be converted into high energy density carbonaceous fuels, liquid fuels, and feedstock chemical. And this is the key aspect of this process. This is the reason why this process is so important and with great perspectives. Of course, there are significant challenges.
Yes, and coming to challenges, of course, there are other technologies that convert CO2 to renewable fuels, such as the catalytic conversion of CO2, so thermal catalytic conversion of CO2 using hydrogen. So what would you say, why electrolysis of CO2 and water are so actively studied in parallel to the catalytic conversion of CO2 and hydrogen?
Thank you. I would like to point out to put into evidence that low temperature co-electrolysis or electrolysis of CO2 and water allows to convert renewable energy into the so-called e-fuels. There is a strong interest, especially the European Commission, regarding e-fuels. These are essentially renewable, based on renewable synthetic fuels. And this is a relevant aspect. Another aspect is that this process can also convert the CO2 and water into commodity chemicals, into feedstock chemicals. And this occurs in a single step without a need to arrange several processes as it occurs with catalytic conversion. Just to give an example, in catalytic conversion, in alternative processes, there is a need to produce green hydrogen in a first step. In a second step, this green hydrogen is used to convert CO2 into syngas. And in a third step, eventually final Fischer-Tropsch process can be used to get high energy density, high molecular weight hydrocarbons. Using low temperature co-electrolysis of CO2 and water can achieve these high molecular weight hydrocarbons in a single step. So this is the key aspect. Regarding this comparison, we can say that the low temperature electrolysis of CO2 and water can save energy and reduce capital costs. And the key aspect is that this process can, in effect, produce multicarbon compounds. That means high energy density synthetic liquid fuels. And this will help a lot in the transition towards a sustainable energy system. And I can say that these are relevant advantages also compared to high temperature co-electrolysis of CO2 and water in solid oxide devices, because in that case we can get mainly syngas. And of course, this syngas should be converted into methane using a downstream catalytic process. And still we have methane as gas, not liquid fuels. So there are significant advantages of using low temperature electrolysis of CO2 and water.
Yeah, this is definitely a significant advantage. And looking at the Fischer-Tropsch conversion, looking at the water electrolysis, these are already mature technologies. So which would be the key performance indicators that provide evidence that the CO2 electrochemical conversion process is competitive to against the green hydrogen production by electrolysis?
Yeah, it is necessary to identify specific key performance indicators that can indicate clearly that the CO2 recycling, low temperature electrolysis of CO2 is competitive not only versus green hydrogen production, but also versus alternative catalytic processes. What is really important is the achieving a high Faraday efficiency for the conversion of CO2 and water into high energy density synthetic fuels, essentially multi-carbon compounds with high molecular weight. This is the first aspect. The second aspect I would like to mention is high energy efficiency. High energy efficiency is also requested because of the high cost at the moment of the high cost of renewable electricity. And this is the second aspect. The third aspect is a suitable voltage efficiency, which is needed to avoid corrosion or degradation processes. So we need to combine at least these three relevant aspects to get an efficient process. I would also like to mention low capital costs. Low capital costs are essentially needed to implement this technology to allow wide-scale deployment of this technology. And these low capital costs can be achieved by operating the device at high current density and also avoiding critical raw materials. Of course, if you operate an electrolysis process at high current density, you have a corresponding decrease of efficiency. So a trade-off is necessary, but this is important. Operating at high current density can significantly decrease capital costs because we can proportionally increase production rate. And of course, I would like again to emphasize about the production of high energy density synthetic fuels like liquid carbonaceous fuels. And this will play an important role for a progressive transition towards a decarbonized or if you want a sustainable energy system with important implications for mobility and energy storage.
Understood. So, but if I look now, coming back again to the maturity of this technology, if I look now into the scientific literature, I see a variation of results, and everybody who's investigating CO2 electro reduction is reporting different products, is reporting different efficiencies, even over different catalysts and so on. So why low temperature CO2 conversion is so much affected by experimental operation conditions, and which physical variables and cell configurations play a role in your opinion?
Thank you for this question. This is an important aspect that should be, of course, addressed properly. We know that carbon dioxide is a relatively inert molecule at low temperature, at low operating temperature. So, of course, converting carbon dioxide at low temperature is characterized by significant advantages, as mentioned before, but this is, of course, this sluggish electrochemical conversion is an important drawback that should be properly investigated and studied. So the electrochemical conversion of carbon dioxide at, let's say, at ambient temperature, at a relatively low temperature, is essentially not just a matter of the selected catalytic systems, but there are also some other relevant aspects that can affect the process, the reaction kinetics, the stability, the conversion efficiency. So these aspects are essentially the operating potential window that can affect the selectivity and the operating temperature and pressure. You know that temperature usually enhances reaction kinetics. Pressure is also important to enhance carbon dioxide solubility. And also there is a strong effect from the type of the electrolyte and the pH. Usually an alkaline environment is preferred because, of course, we want to solubilize CO2 at the interface between the electrolyte and the electrode. And I think that significant progress has been achieved from, when gas diffusion electrodes and flow cells have been started to be have been investigated for this process. These two approaches have allowed to increase significantly the productivity. Of course, I have to say that as well now, aqueous electrolytes can promote hydrogen evolution. That unfortunately is a competitive process, but sometimes we need aqueous electrolytes to reduce ohmic drop. Organic electrolytes can have, can avoid hydrogen evolution, but at the same time, we need the water, and also we need to keep low the ohmic resistance. So accordingly to these observations, there are advantages and drawbacks by selecting specific operating conditions. Usually bicarbonates of sodium and potassium allow to increase the carbon dioxide solubility at the interface. And the same, I would say, it occurs for ionic liquids. However, here there is of course, the cost should be taken into consideration in the latter case. What is also interesting to mention is that reducing the by using a more negative electrochemical potential, we can produce, of course, methane, ethylene, methanol, and of course, from a thermodynamic point of view, carbon monoxide and formic acid would require a more negative potential. However, despite of these thermodynamic aspects, carbon monoxide and formic acid are preferentially produced in some cases because these are two electron processes instead of methanol or ethanol. And methanol is a 6 electron process. So, of course, there are several aspects to consider: thermodynamics, reaction kinetics, and of course, selection of proper operating conditions and cell configuration of gas diffusion electrodes play an important role for this process.
So I see that the electrochemical conversion of CO2 can result in a lot of products, and depending on the variables, depending on the operation conditions, a lot of products can be produced and at the different efficiencies. Now, coming to these different products and the reaction kinetics, of course, the reaction kinetics are especially driven by the type of electrocatalyst. And so what would you say, which electrocatalysts are the most effective for this process? Let's say for our carbonaceous fuels, whether liquid or gaseous.
Thank you. This is, of course, an important aspect, the selection of the best electrocatalyst for the desired process. And in the case of the ECO2Fuel project, our aim is to achieve carbonaceous fuels. Of course, to achieve efficient reduction of carbon dioxide and water, what is needed for the electrocatalysis is a high activity, proper selectivity, and low overpotential for this process. These are the main aspects, in my opinion. Why the main aspect? Because these are linked to the production rate. High activity means high production rate. Proper selectivity means high Faraday efficiency towards carbonaceous fuels, and low overpotential means high energy efficiency. So these are the most important aspects. Of course, we need to play around with the catalyst chemistry, composition, morphology, oxidation state, crystallographic structure, surface properties. So designed an efficient catalyst and selective catalyst is, of course, required to address all these properties. Just to give some examples. Regarding the morphology, it is well known that the high surface area is desired to achieve practical conversion rates. And regarding the chemistry, I will give some practical examples. As an example, silver-based electrocatalysts are extremely effective for carbon monoxide production with high Faraday efficiencies. But if we want to obtain not syngas, not carbon monoxide, but multicarbon compounds, carbonaceous fuels, multicarbon based, we need copper oxides. These are the most important catalysts for producing these high molecular weight carbonaceous fuels. Why? Because copper has the lowest binding energy for carbon monoxide adsorption. So, of course, carbon monoxide that is adsorbed on the surface can react, and of course, we can have carbon-carbon coupling. Crystallographic structure is essential to achieve effective carbon-carbon coupling, because we need the neighboring copper sites in order to maximize this process, in order to achieve multi-carbon compounds like ethylene, like ethene, like ethanol, and so on. So it is important to select the proper copper oxide electrocatalysts if the aim is achieving multi-carbon compound. However, the oxidation state on the surface play an important role. As an example, if we have a copper 2+ on the surface, in principle, the process can provide essentially methane, but this never occurs because in principle, when you apply a reducing potential, you have a partial change from 2+ to 1+ to metallic copper. And of course, I have to say that the mixture of different copper oxidation states is favorable to obtain multicarbon compounds. Instead, metallic copper can promote hydrogen evolution or in parallel carbon monoxide or formic acid formation. So if the aim is to achieve multi-carbon compounds, we need to play around the copper oxide oxidation state. We need to avoid strong reducing potentials to avoid formation of metallic copper. And this is also essential to achieve high energy efficiency. In principle, an important aspect is also combination of different catalyst formulations, like combining copper oxides and silver. And of course, silver can can promote formation of carbon monoxide and syngas, and this syngas is converted through the copper oxides to multi-carbon compounds. So also the combination of electrocatalysis can play an important role. Of course, I would like also to mention some alternatives to these well-known catalytic formulations. I would like to mention molecular electrocatalysis based on metal ligand complexes of iron porphyrins, polypyridyls. Also would like to mention carbon nanotubes. Would like to mention nitrogen doped carbons, avoiding completely transition metals, also single atoms of like zinc, nitrogen anchored zinc on carbon, also molybdenum selenides and sulfides. Of course, the selection of the catalyst chemistry depends on what kind of products we want to achieve. And I would like to say that, of course, not only, let's say, productivity, but also stability is extremely important because we want to achieve good performance at the beginning of life, but we also need good durability in order to make this process highly reliable. And I have to say that the catalyst poisoning by adsorbed organic residues is a relevant drawback at the moment, affecting the durability of this process.
So I understand that the selectivity of the products very much depends on the, or as you maybe depends on the surface chemistry. So you said that the surface chemistry of, for example, copper, if we are operating at high reducing potentials, it will reduce back to copper, and then we will preferably get either hydrogen or carbon monoxide. Now, we want to go to higher molecular weight products. So, what would be the idea of you to prevent this high reducing potentials, but at the same time operating at high current densities?
Thank you. This is a critical challenge. We want to achieve a high selectivity towards high molecular weight hydrocarbons. And of course, we also need to operate at high current density. That means also high productivity. And of course, selectivity has a strong impact on Faraday efficiency for the formation of the desired organic fuels in competition to hydrogen evolution. Of course, we need to stabilize the desired oxidation state. As an example, the oxidation state of copper oxide can be stabilized by addition of zinc, by let's say, we'll say by formation of solid solutions with other metals, and eventually with by anchoring these on a specific support. So it is important to stabilize the oxidation state on the surface with regard to the specific process. This is an important, we'll say, aspect. And of course, we need to mention that the selectivity is governed by the reaction mechanisms. So the reaction mechanisms are affected by the catalyst properties, as mentioned, the oxidation state, the sulfur properties, the chemistry, but also the reaction environment that this was discussed at the beginning of our, let's say, conversation. The reaction environment can also drive the process towards specific directions. And how to deal with all these variables. Of course, several scientists use atomistic simulations, functional density theory studies in order to get relevant insights into the reaction mechanism. And this can reduce the number of iterations, or can reduce the time-consuming trials and errors approach. So the process, the reaction mechanism is, of course, complex, but we have some tools to identify proper routes to enhance the conversion of carbon dioxide and water.
So I imagine all these variables, or controlling all these variables, is very, very challenging. It's time consuming to get to a point where we can actually produce with high selectivity a certain product. Going to the products and the control of the whole process, one could imagine that it is very, very also cost intensive. So we have been discussing now in the European at the European level, but also in Germany, and I'm also sure now also in Italy, where you are situated, that e-fuels are very not very cost effective. So they are very expensive, and people that are in favor of e-fuels, for example, for mobility, they are always like, so people like to discuss very controversially about this topic. So what would you say, how to reduce the cost of the produced e-fuels from CO2 conversion, and which would be the main drivers to do that?
Yeah, this is, of course, an important argument, the cost of the of the produce of the e-fuels, because at the end of the day, we need to produce synthetic fuels with at a reasonable cost. I would say that the main drivers that affect the cost of e-fuels are at the moment primarily the cost of renewable electricity, and also the capital costs of the system, but also the uptime hours. The cost of renewable electricity is at the moment still high. Let's say the target will be to achieve, let's say, a cost for renewable electricity lower than 40 euro per megawatt hour. And regarding the the capital cost, of course, it is also have a significant effect. We need to reduce the capital cost by increasing operating current density. It doesn't make any sense to operate such system at a low current density, because of course, in that case, we have a low production rate, and accordingly, we have a high capital costs. Coming back to the cost of renewable electricity, how to address this aspect? By increasing efficiency. Of course, if we increase efficiency, above 80%. This is the target. We can, of course, minimize the amount of renewable electricity that is used. And regarding the uptime hours, of course, we have here to consider two possibilities, grid connected systems or let's say standalone systems connected just to renewable power sources. Of course, we want to maximize uptime hours, because if we keep off the system for, let's say, several thousand hours per year, of course, we stop the production, and of course the cost of the produced e-fuels will increase. So what is really important is to reduce the cost of renewable electricity by, and the production of e-fuels can act as an incentive to increase the installation of renewable power sources. We need to operate the system at high current density, because of course this has a direct impact on capital costs, and of course identify strategies regarding the operation. Regarding the durability, this is another important aspect. Of course, durability durability is necessary in order to, let's say, manage what is payback period. When you have such kind of investments, you have a payback period in, let's say, 5-8 years. We need eventually to reduce capital costs in order to have a payback period after 2-3 years, essentially, and of course have strong durability in order to operate the system for 20 years. So also to get some economical advantage. And other aspects are also related to the pretreatment of carbon dioxide, to the pretreatment of the flue gas scrubbing and purification from sulfur compounds will play a key role regarding durability. So it is not just important to focus on the system, on the operating conditions, but also on the, let's say, surrounding aspects, on the pretreatment of the flue gas. These are also relevant aspects.
So that makes a whole lot of different drivers that we need to optimize in order to bring down the cost for e-fuels from CO2 conversion, which are mostly also not in the power of the company who would build the ECO2Fuel system, but may also be dependent on other external drivers. But so when I listen to CO2 electro reduction conversion technologies and seeing how far they have progressed, I come to the idea that the CO2 electrochemical reduction to e-fuels may be the holy grail, and the answer to our problems, climate problems. So what is your perception? Do you think that the CO2 recycling is perceived by the general public as a possible means to reduce greenhouse gas emissions? Because sometimes I hear very controversial discussions, and how to enhance, how would you think would be the best way to enhance the social acceptance of the CO2 electrochemical reduction?
Thank you so much for this question. This is an important aspect. In my opinion, the CO2 recycling is essentially perceived by the general public as an important opportunity to progressively decrease the net emissions of CO2 into the atmosphere. Recycling strategies are gaining momentum, so this is, of course, an important approach. So, in my opinion, it is clear to everybody that fossil fuels must be avoided in order to manage with these climate changes and global warming. But at the same time, this is also perceived as a risk for the security of energy supply. So, in that regard, in my opinion, information campaigns about the perspectives that is offered by the CO2 reduction in assisting a progressive transition towards a decarbonized energy system is extremely important. And of course, we need to show through this information campaign that this will not have a dramatic impact on the content and the availability and the available amount of energy and related uses. And this will be extremely important to increase the social acceptability. We need to clarify that carbon dioxide recycling is one of the best approaches in the transition period towards a complete decarbonized energy system. But in my opinion, this can go also beyond the complete decarbonization because we will still use some carbonaceous fuels in some industrial applications. So we think that this sustainable process will be important not only for the transition period, but also once the significant decarbonization is achieved. Uh, it should be made clear that there is no competition between green hydrogen and synthetic fuels, since both green hydrogen and synthetic fuels contribute to make sustainable our economy. So we think that we need to focus on both aspects, on both processes. And of course, it should be made clear to the general public that there is no competition between water for electrolysis and fresh water for agriculture or potable water for the citizens. This is an important aspect. At the moment, this technology covers just a niche market. And since it covers a niche market, fresh water is used. However, uh, in the next years, we expect that this technology will be deployed on a large scale. And in that case, desalinized and wastewater will be used instead of fresh water with with the minimal impact on energy efficiency, because there are at the moment efficient desalinization process based on, let's say, reverse osmosis as an example, or evaporation processes. So this is not a problem. The availability of water is not a problem because in the future we will not use any fresh water for this process, but seawater and wastewater. And of course, using wastewater, there is another important advantage because using this process at the cathode, we reduce CO2 to carbonaceous fuels. At the anode, we can oxidize the organic contaminants that are present in wastewater. So, using the same process, we can, in principle, get fuels, e-fuels, and purify the water. So this is an important aspect to mention to the public, to the general public, to the society. It is also an important aspect that using seawater, of course, we can get the water for the electrolysis process and the minerals, remaining minerals. We can extract the minerals for several applications, like for lithium and sodium batteries or for several other applications. So there are important applications of this process in the future using seawater and wastewater, and it is important to communicate these aspects not only to the general public but also to the policymakers, because of course there are significant advantages, and we need to, let's say, start with the demonstration projects on a large scale, provide specific support to research in order to advance in this field.
So, listening to your latest ideas, where you could really make a CO2 electro reduction on the cathode side to produce e-fuels, and on the anode side to even clean up the wastewater, such a system would be really all-rounder. So you could actually use it for everything. But one critical question at the end, since we are coming to the end, the question is, so whenever I talk with people outside the consortium about CO2 electro reduction, I always hear one question, and this question is, isn't the CO2 reduction, so converting the CO2 to e-fuels, isn't that and later on burning the e-fuels to convert it back to energy, isn't that just a delaying of the CO2 emission? And that's the last question I would like to ask you. So it's a critical question, which I always hear, and I would like to have your opinions on that.
Thank you so much for this question. What we need to emphasize is that this is a carbon neutral process, because of course we can take carbon dioxide from the process at the moment producing this flue gas, and convert this into e-fuels that are used in internal combustion systems, or also in high temperature solid oxide fuel cells at high efficiency. At the end of the day, there are no net emissions of CO2 into the atmosphere. So this CO2 recycling is a neutral carbon cycle. So what we need is to avoid increasing carbon dioxide emissions into the atmosphere. But there is also some other process that is carbon negative. As an example, if we recycle carbon dioxide to produce organic compounds as feedstock chemicals for, let's say, producing plastics like methanol. Methanol is a feedstock chemical. In that case, we can have a carbon negative process. We can try to use these processes also to produce commodity chemicals. In the future, probably we still need some carbon compounds for some specific applications. So the chemical industry will need some carbon compounds, some feedstock chemicals. So in that case, we can have also carbon negative processes. I will say that, as already mentioned, this is not just important for the transition period up to achieve complete decarbonization of the energy system, but can continue after the decarbonization, because CO2 carbon compounds cannot be completely excluded from our economy. And what is really important is to have a carbon neutral process without net CO2 emissions into the atmosphere. And the other aspect is also having a carbon negative processes. So this is my opinion. This process will have significant perspectives, not just for the transition period, but also beyond the transition period.
Great. Thanks a lot, Antonino. So if I understand you right, as long as we stop using new fossil fuels and keep recycling the CO2, we can make it either CO2 neutral or CO2 negative. Great. Antonino, thank you very much for the time that you took and answering this quite challenging questions. I learned a lot in this session with you, and I wish you a very nice day, and I hope to talk to you soon.
Thank you very much, Schwan, for this opportunity to discuss with you, and of course for the collaboration in the ECO2Fuel project. And I expect we can achieve significant progresses. Thank you so much.
Thank you, Antonino. See you soon. Bye.
We'll be back soon with more thought-provoking discussions and groundbreaking discoveries. Until then, remember that every small step towards sustainability counts. Let's continue to explore, innovate, and transform our world for generations to come. ECO2Fuel Perspectives is a production of the ECO2Fuel project under Horizon 2020's Green Deal program. To learn more about the project and access additional resources, visit our website at www.eco2fuelproject.eu.